In this video, I would like to develop a tool that we'll be able to use for estimating the size of the complex integral that we work with. It's going to be a very important tool for proving very important theorems in this topic. So let's get right to it. Okay, we'll start by looking at the arc length of the path itself. So let's say gamma is any smooth curve. We can compute its length by estimating the curve by lots of intermediate points, and then measuring the straight line distance between the intermediate points, and so on. And then finally adding them up. Now that won't be exactly the length, but if we subdivide the curve to finer and finer intermediate points, then we'll get something that's very close to, or in the limit, exactly the length of the curve. So what would that look like? So we want to take the limit, where n is the number of intermediate points we want to use, and compute the magnitude between the difference of the intermediate points. Now, if we do that, we can multiply top and bottom by the difference of the time parameter for the curve that corresponds to those intermediate points. And then now, this portion becomes the derivative of the curve, or I guess the magnitude of the derivative of the curve. And this portion becomes the dt of the Riemann integral. And basically, we can get the arc length by integrating of the magnitude of the derivative of the curve. Okay. When this limit exists, we say that the curve is rectifiable. So that just means it's a smooth curve that has a finite length. Okay, let's do an example or two. So if we look at the curve big R times e to the it, so this would be a circle radius big R. So the derivative is going to be RI EIT. And if we take the magnitude, right, so the constant R I could just pull outside of the magnitude, and I has magnitude of 1. E to the it also has magnitude of the 1. So the magnitude is fixed constant R. So we're just integrating R from 0 to 2 pi. So the arc length is going to be 2 pi R. That's the circumference of a circle radius R, right? Okay. Another example. If you have a curve t plus it, the derivative is 1 plus I, and the magnitude is going to be square root of real part squared plus imaginary part squared, square root of 2. So the length is going to be from 0 to 1 root 2 dt. So the length of this curve is square root of 2. Okay. All right. So now I want to move on to something that's building on top of this. I want to define a notion of integration with respect to the arc length itself. So this is different from the path integral, but it's similar. What we do is we integrate along, so we denote integration by arc length by putting the absolute value sign or the magnitude around that, the dz. So basically what we're doing is we're going to say f of gamma of t as what we do in path integral. We also multiply by the derivative, but not just the derivative. We're going to take the magnitude of the derivative. So you don't care too much about the direction where the curve is heading when you do this, although the value of the integrand does matter. Okay, so this is a slight generalization of computing arc length, because the arc length itself is basically integrating one with respect to arc length. Because I mean, if you replace the integrand by one, we just get the formula for the arc length itself, right? And if you multiply by some other function, you might get some other value. So here, let's integrate the function z on a unit circle. Magnitude of z equals to 1. So right here, I'm abusing the notation a little bit, right? What I mean by that is I'm going to take a curve that traces the unit circle counterclockwise. But this is actually a shorthand that's used frequently in complex analysis. So I'm going to use it just so you, even though it's not quite the right notation, right? Like I should be writing the curve itself there. But I'm going to use it because literature uses it as well. Okay. So the curve e to the it traces the unit circle counterclockwise, going from 0 to 2 pi. Here's the derivative. The magnitude is 1. So this part really disappears from the integrand. The antiderivative of e to the it is 1 over I, e to the it. But if you plug in 2 pi or 0, e to the 2 pi I and e to the 0 is both equal to 1. So we get 0 in the end. Okay. All right. So this is the main tool that I wanted to get to in this video. It's called the ML estimate. So here's what it looks like. So if we want to estimate the size of this complex integration, some path integral, then that's going to be whatever that is going to be less than or equal to if we integrate the magnitude of the complex function inside and integrate it with respect to arc length. So the notation for the integration with respect to arc length is kind of helping with this idea of this ML estimate. So let's think why this would have to be true. Okay, and actually, I could go a little bit further than that. In particular, if we can find the maximum value or some number that's bigger than the maximum or the modulus of the inside, so make a very crude estimate of what the function could be, how big it can be, call it m. Okay. Then if it's a constant, we could just pull that outside of the integral, and we can compare it with m times the length of the path itself, right? And it's called ML estimate because m for this maximum value that we use and L for the length. So it's telling you exactly how you estimate it with the maximum value and the length. Okay, let's look at how we might use something like this. So you have a curve gamma t plus it and some function z squared. And we want to estimate how big this can be. Well, we can estimate it by first estimating the maximum value the inside can be. Well, we're looking at the value z squared, and the path looks like this. Okay. So the modulus of z squared is the modulus of the distance from the center squared. So the largest it could be, the z squared, is right at the end of in the path itself. So the modulus of 1 plus I is square root of 2. So the modulus of square root of 2 squared is going to be 2. So that's my m in the ML estimate. And then the arc length of this path is square root of 2 as well. So that's the length, square root of 2. So if I didn't want to compute this integral, then we can make a rough estimate of how big, at least in modulus, the result of this integral. Okay, I hope that makes sense. And how you might prove it? Well, the path integral is going to be, let's see. Okay, the path integral looks like this. And then we're taking the absolute value of everything. Okay. From the Riemann integral, we know that, let's see, we can estimate the inside area by the maximum value that the function takes. So this is going to be less than or equal to m, and we multiply by the length of the path itself. And this is exactly what we have. Okay, so the m we can pull out outside of the integral, and then the rest of what we have is going to be the arc length. Okay. This will be important in future theorems that we're going to prove. So keep in mind, like, kind of carve it into your head that this is a very important estimate. In fact, it's so important that I'll guarantee you that it'll appear in the final. Okay. Anyways, I will see you in the next video.